Howdy. 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 Konnichiwa. Konbanwa. Howdy. I don't know. I just thought of I don't know what konbanwa means. Just know it's some kind of a greeting. I actually took Japanese in high school for 2 years and the teacher was so bad. Probably the worst teacher I've ever had now that I think about it. Um, One time I remember this. It was at the end of the year, okay? And the teacher, so we all had our yearbooks and we were supposed to be paying attention, but this one kid was um, signing yearbooks, okay? And he flipped out and he went over to the guy's desk and he grabbed his yearbook and he literally just took it and like slam dunked it into the trash, and the yearbook actually ripped in half. And then everyone was just like, "Oh, I can't believe what just happened." Um, that was the stuff you could get away with back in the early 2000s. Still keep your job. I probably couldn't slam dunk anyone's yearbook and keep my job. It's not fun anymore. I want to be able to slam dunk yearbooks. No, no, he didn't have to pay for it. He just shouldn't have been signing yearbooks in class. All right. So this is going to be our last momentum lecture, and I'm going to have a little theoretical exposition at the end that I hope you will enjoy. So today's lesson is about something called impulse. Okay, impulse is denoted by J. It is a vector, and it is equal to the integral of the force of a force vector with respect to time, from t initial to t final. Okay. So this is integrating a vector. I will teach you in a moment how to integrate a vector. It's very simple. Okay. But it's it's the integral of a vector, and the impulse is a vector. The units of impulse, well, it's a force times a time, so it's going to be Newton seconds. All right, so that is impulse. An alternative way to think about impulse is, because this is an integral, integrals are area under the curve. So if you have a force time graph like this, okay, the impulse is the area under that force time graph. Okay, so these are two sort of equivalent ways of thinking about impulse. So why is impulse worth defining? That's a good question to ask. Why is impulse worth defining? To understand why this is something that is worth defining and talking about, actually, I'll be straight up with you. Impulse is very rarely used in physics, but it is on the AP and the IB exams. Okay, I've spent very little time thinking about impulse. It's used in rocketry. It's used a little bit in astrophysics, but that's pretty much it as far as I can think of. It's just not really necessary to use it that often. But let's go to the sneaky form of Newton's second law. Okay, so I in the very first momentum lecture, I discussed the sneaky form of Newton's second law, which is net force, okay, equals the derivative of the particle's momentum. That is the sneaky form of Newton's second law. So to understand why impulse is worth defining, let's integrate the left-hand side and the right-hand side with respect to time from t initial to t final. Okay? So on the left-hand side, we have the impulse due to the net force. Okay? On the right-hand side, we're integrating a derivative. So remember, integration and derivatives are reverses of each other. So if we integrate the derivative of the momentum, we just get back the momentum. Okay? And actually, because it's final minus initial, it's going to be the change in momentum of the object. So that's kind of the fundamental theorem of calculus, if you will. So this is probably our main result for today. And what it says is that the impulse due to the net force, that's important, is equal to the change in momentum of the object. Okay? So that's basically one of the uses of it. Okay? So I mentioned the impulse is sometimes used in astrophysics, and I can remember, I can probably find the textbook. You know, it's funny because I took the class that used this textbook when I was, I think, a junior or a sophomore in college. And this might be the only time that I've seen impulse used in a textbook. So let me try and find it. I should read this book again. This had a lot of good stuff in it. Okay. So, yeah, you can see, I don't know if you can see that, but integral of the force with respect to time, okay? And it was used for one star, or a planet, or a comet or anything. You have one astronomical body going by another astronomical body, and it's going to get deflected. Its momentum is going to get changed. And so you can use impulse to figure out by what angle it's going to get deflected. Okay. That was a bit of an aside. So what I want to talk about is, for just a second, is impulse versus work. So these are two different things, but they're kind of closely related. So if we think about impulse, J is a vector. It has a magnitude and a direction. Okay. Work, on the other hand, is a scalar. So impulse, if you have something in two dimensions, impulse has an I and a j component. If something is moving one-dimensionally, then we don't worry about i's and j's. But impulse is a vector. Work never has I and j components. Okay. The net impulse is equal to the change in momentum. The work kinetic energy theorem says that the net work is equal to the change in kinetic energy. All right. So we can see that impulse is to momentum kind of what work is to energy. Okay. Similarly, if you have a force time graph, the area under the curve is impulse. If you have a force versus position graph, the area under the curve is work. Okay, so they're very similar, but they're not quite the same thing. Okay, so you need to know the difference between the two, or else you might get confused in certain situations. Okay, so we're going to do some examples. Let's suppose we have a force is given by f of t, so it's a force that is a function of time, equals 4t squared times I hat minus 7t times j hat, and it acts from t equals 0 to 1 second. Calculate the impulse. Okay, so the reason that we're doing this example is that I want to show you how to integrate a vector. Okay, so the impulse is the integral of the force with respect to time. So that's going to be the integral from 0 to 1. Okay, so now I'll substitute in my specific force function. So I have 4t squared I hat minus 7t j hat. Okay, and when you are integrating a vector, you just treat I and j like constants, because they are constants. They always point in the same direction. So what that's going to be is, so this basically becomes two integrals. The integral from 0 to 1 of 4t squared dt times I hat minus the integral of 7t dt j hat. There's a question. So they're related in that one is comprised of exclusively vectors and the other is exclusively scalar. So impulse is a vector, and it's going to have I and j components unless it's one-dimensional motion, because in one-dimensional motion, there's only one direction. So there's no need to really differentiate between vectors and scalars, okay? But if you have something that's two-dimensional, then impulse is going to be a vector, okay? So doing this integral, I've got to bump up the power and then divide by the bumped up power, and then evaluate from 0 to 1. And then bump up the power by 1, divide by the bumped up power, and evaluate from 0 to 1. Okay, so that's going to give me 1.3 I hat minus 3.5 j hat, measured in Newton seconds. So that is our answer for the impulse. All right, so that's an example of how you integrate a vector. Let's do another example. Suppose we have a 3 kilogram object with velocity 9 meters per second in the eastward direction. And it experiences a net impulse, and that's important to say net, of 40 Newton seconds in the northward direction. What is the speed after? So this is an example of an impulse problem where the two-dimensional nature is important, okay? So if I make north-south along the j direction and east-west along the I direction, by saying that the impulse is 40 Newton seconds in the northward direction, then that means that j net is 40 j. Okay. For the initial momentum, we have momentum is m times v, so 3 times 9, that's 27 in the eastward direction, so that's the I hat direction. So P initial is 27 times I hat. Okay. P final, we know that the mass of the particle is 3, but its final velocity is unknown. So now I'm going to use that formula that J net is equal to delta P. So that means that 40J, so 40J is on the left-hand side, is equal to change in momentum. Change in momentum is P final minus P initial. So 3 V final minus P initial, so minus 27 I hat. Okay, we're trying to solve for V final. So I add 27 I hat to the other side. 27 I hat plus 40 j hat equals 3 v final. All right. Divide both sides by 3, and I get 9I plus 13.3 j is the final velocity vector. But I did not ask for the final velocity vector. I asked, what is the speed after? What is the speed after? So we have this final velocity vector that goes over 9 and it goes up 13.3. And the speed is the hypotenuse of that. So the speed is going to be square root of 9 squared plus 13.3 squared. And that works out to be a final speed of about 16 meters per second. Okay? Let's do another example. Suppose we have a net force versus time graph. Okay, so we have the net force in newtons, and we have the time in seconds. This force, it ramps up from 0, and then at 3 seconds, the force suddenly drops to nothing. The maximum force that is achieved is 100 newtons. Okay? This net force acts on a 4 kilogram particle initially at rest. Okay, 4 kilogram particle initially at rest. What is the final speed? So what we want to do first is we want to calculate the impulse. So 1/2 base height. This is a triangle. So the area of that triangle is going to be 1/2 times 3 times 100, which is 150 newton seconds. Okay, so I'm going to use J net equals change in momentum. Change in momentum is P final minus P initial, but because the particle is initially at rest, P initial is 0. So we have the final momentum is 4 times whatever the final speed is. The impulse is 150. Divide both sides by 4. We get that 37.5 meters per second is V final. All right. We're going to do one more example, and then we're going to have a super sweet theoretical exposition, let me tell you. It's going to give you goosebumps. It's so good. All right. This example actually has to do with the sneaky form of Newton's second law. So what if we have a floor, or just a wall, okay, and we have a 2 kilogram particle, and the 2 kilogram particle goes dunk, dunk, like this, okay. The initial velocity of the particle is 5I minus 3J meters per second. So you can see that the j component is negative because it's going down to the wall. Okay. Now what's going to happen is when it hits the wall, is now its velocity is headed upward. So now it's going to have a plus j component. And we'll assume that the collision was not perfectly elastic, and so it actually lost some of its vertical speed. Okay, so if it were perfectly elastic, it would bounce up with a 3 plus 3j of vertical velocity, but we'll say that it wasn't quite elastic and it only bounces up with plus 2j. And then there's a little bit of friction when the ball hits the wall, and that slows it down horizontally as well, so that's the final velocity vector. You use some ultra slow motion high-speed photography camera, and you can actually see how long the ball is in contact with the wall. Ball is in contact with the wall for 0.01 seconds. You would only be able to tell that if I don't know what that slash means. Why did someone type this? Oops. Oh yeah, you're right. It should be 4i. The is with the save. All right. So let's estimate, and that's a keyword, estimate the force of the ground, or of the wall, on the ball. Okay? So what we're going to do is we're going to use the sneaky form of Newton's second law. Net force equals the derivative of the momentum. But because I said estimate, when you estimate a derivative, remember the derivative is a limit as delta x goes to 0, or a limit as delta t goes to 0. But if you don't let delta t go all the way to 0, you can approximate the derivative. Okay, so this is going to be approximately equal to just change in momentum over change in time. Okay. So the final momentum is going to be m times v. So that's going to be 2 times this, which would be 8 I hat plus 4 j hat. So that's my my final momentum. The initial momentum is going to be 2 times this, so 10I minus 6 j hat divided by 0.01. All right, so let's do the subtraction. I have 8I minus 10I, that's minus 2I. And then I have 4I minus 4j minus 6j. So that's going to be 10j. And all this is divided by 0.01. Okay. It's the same thing as multiplying by 100. So I have 200I plus 1000j newtons. And that's the approximate value of the force that the wall exerts on the ball. Okay? So we're going to do a little bit of theoretical exposition at this time. And it has to do with rocketry. So I'm going to teach you, I'm going to derive what is called the Tsiolkovsky. I don't know, some Russian guy, so I'm just going to put SP. I'm not sure how to spell his name. Rocket equation. Okay, so we're going to derive it, the rocket equation. So here's the scenario. We've got a rocket. Here's the rocket. Okay, and we're going to imagine that the fuel is inside the rocket. Okay, so this is the rocket right here. And this is the fuel that is inside the rocket. Okay, so the total mass of the fuel and the rocket is m. And then the initial velocity, this is going to be one-dimensional, by the way. The initial velocity is v initial. Okay? And then we're going to consider what happens a short time later. Now, as a rocket propels itself, it sprays fuel out the back. Okay? So, a short time later, the rocket has sprayed that fuel out the back. So now the fuel is out here. Okay? And as a result of that, the rocket now has a speed v initial plus dv, where dv is a small number that represents how much the velocity increased over that short time interval. Okay? The fuel is, it has less forward velocity than it has had before, or it might even have a negative velocity, but how do we determine that? Well, it's going to have its initial velocity, but then it has an exhaust, okay? So the velocity is reduced by the velocity of the exhaust. Because when a rocket is launching, the exhaust is sprayed backwards with a certain speed, okay? Now, what would happen if a rocket flew by and its speed was exactly equal to the exhaust speed? What you would see is that the exhaust would just be stationary with respect to you, okay? I hope that makes sense. So the velocity of the fuel is reduced by the exhaust speed, okay? Now let's talk about mass. The mass of the rocket is going to be m plus dm, where dm is actually going to be a negative number, okay? Because the rocket was sprayed out some fuel, and so it has lost mass, okay? And by conservation of mass, the fuel has a mass negative dm. So if we look at the total amount of mass is going to be minus dm plus m plus dm. So those two cancel out, and we just get that the total amount of mass stayed constant. Okay? So let's write an expression for the initial momentum of this system. M times v naught. Easy. Let's write an expression for the final momentum of the system. The final momentum of the system is going to be consisting of two parts, mv for the fuel, for the exhaust, and mv for the rocket itself. Okay? So for the rocket, its mass is m plus dm, and its velocity is v plus dv. For the exhaust, the mass is negative dm, and the velocity is v naught minus exhaust velocity. So this is mv plus mv, all right? And momentum is conserved, all right? So what I'm going to do on the right-hand side is I'm going to multiply everything out all the way. So I'm going to multiply this through. So I have minus dm times v naught plus dm times velocity of the exhaust. And then I'm going to FOIL this term. So I have first, oops, that should be v naught plus dv. My first is going to be m v naught. My outside is going to be m dv. My inside is going to be dm times v naught, and my last is going to be dm times dv. Okay? Now what we notice here is that a lot of these terms are canceling out. So I have mv naught here, and I have mv naught there, so on the opposite side. So those two cancel each other out. All right? Here I have minus dm times v naught. Here I have plus dm times v naught. So these two cancel each other out. And lastly, here we have dm times dv. Now because we were looking at this a short time later, the amount of mass that is lost by the rocket is very small. And correspondingly, the amount of velocity increase is also very small. So what that means is that this term is a really small number times a really small number. And a really small number times a really small number is approximately 0. So we're going to neglect that term as well. All right? So we're only left with two terms. It's just this one and this one. So we have dm times the velocity of the exhaust plus m dv. I'm going to rearrange this equation. So we have minus dm times the velocity of the exhaust, and then I divide by m. So this is that equation rearranged. Now, I'm going to integrate both sides, keeping in mind that the velocity of the exhaust is a constant and it depends on the particular properties of the rocket booster that you're using. So I integrate both sides from initial to final. And I can see I have this integral of dm over m. So that's natural log. Of m final over m initial. And then on the right-hand side, okay, I have that the change in velocity. So I'm gonna absorb the minus sign into the natural log and then flip the argument of the natural log. So I have v initial or v exhaust times the natural log of m initial over m final is the change in velocity. Okay, so this is called the rocket equation, and it's used extensively in by the appropriate engineers. What we can see, because the whole thing in space travel is all about getting the largest change in velocity possible. Okay, because that's what's going to allow you to go to a different planet or go to a different star or get up into orbit or whatever you need to do. You got to change your velocity. So we can see what makes the change in velocity as big as possible. Okay, we want to have the exhaust velocity as big as possible. Okay. Furthermore, natural log is an increasing function, right? So we want to have m initial over m final should be large as possible. Okay, so as the rocket lifts off, or as it executes a maneuver, it's spraying out fuel, and as it's spraying out fuel, the mass of the rocket is being reduced. And to get the biggest change in velocity, you reduce the mass by as much as possible. So this is the reason why the space shuttle, when it takes off, it's mostly fuel. Okay? You have the giant orange fuel tank, you have the solid rocket boosters on the side. Most of the mass of the thing that is being launched is fuel. And all that fuel gets sprayed out. So the M initial is much greater than the final mass, because the final mass that actually makes it into orbit is just the space shuttle. Okay? So you want to make that as large as possible. Just really quickly, what if we had the velocity of the exhaust is 1,000 meters per second? Okay. And what if M initial was 5 times M final? Okay. So let's just work out the numbers on that. That would be that would mean that the initial mass is 5 times what it actually ends up being. So what do we get for the delta V in this case? We would get 1,000 times the natural log of M initial over M final, which would be 5. Okay. So that gives 1,609 meters per second of delta V. Okay? But what if we made a much bigger rocket? We were like, okay, what if the exhaust velocity is still 1,000 meters per second? So it's the same technology on the exhaust nozzle. But what if the initial mass is 100 times the final mass? So that is a much bigger rocket. That's like adding way more fuel than you had in this first case. So what would we get? We would get delta V is 1,000 times the natural log, okay, of 100. And that gives 4,605 meters per second of delta V. And this right here is why space flight is so challenging. Okay, look at this. You increased the mass of the rocket by 20 times. You increase the mass by 20 times. You're carrying 20 times the amount of fuel, but you only get about 3 times the delta V. So you see how it's not proportional, okay? You could do 1,000 times the mass, but you're not going to get anywhere close to 1,000 times the delta V. So you have these diminishing returns, and it's because of the natural log function. Okay, the natural log function, its slope is very flat, and so this is the reason why it is so difficult to do space travel. This is also the reason why, if we went to, that was not on purpose. This is also the reason why we want to launch things from the moon, because what we can do is we can get into orbit, we can get to the moon. That requires a certain amount of fuel, okay? But then to go to Mars, we can refuel to make M initial over M final very large again, and then we can launch from the moon, and it's gonna. So basically, we're giving ourselves more delta V by refueling. There's a really great question in the chat, which is the natural log there because the more fuel you carry, the harder it is to accelerate? Excellent. That is exactly right. If you think about it, more fuel is going to allow you to do more stuff, okay? But the more fuel you carry, the more fuel you have to accelerate. And so that fuel is less effective. Excellent observation. All right, so I hope you enjoyed that theoretical exposition. None of the questions are going to deal with this stuff. I just wanted to talk about it because it's cool. All right, so that's all I have for today.